Good day, everyone. My name is Abdulakeem Ahmed, a Ph.D. student of the School of Material Science and Engineering of Chang'an University. As the host earlier said, we worked on the preparation and characterization of low flammable asphalt for tunnel pavement. And it's going to follow this plan with the limited time. I'll just focus more on the discussion of the results, basically. So the goal of the research was to create an inorganic flame retardant that could leverage the unique symbiotic relationship between its individual components to help improve the flame retardance of asphalt, especially those used in the pavements, without reducing the normal properties of whatever base asphalt was used for the tunnel pavement. So an orthogonal design was employed with various evaluation indexes to optimize the asphalt, followed by performance tests to check what was the findings of the research. So on the left in the figure 1 is the appearance of the 4 halogen-free chemicals that were used: the expandable graphite, magnesium hydroxide, calcium hydroxide, and ammonium polyphosphate. And to prepare the FRB blend, as we have termed it, the flame retardant blend, it followed this specific preparation process where we, using an orthogonal design and a technique for order of preference and similarity to ideal solution, we optimized the FRB blend and then dried for 2 hours, cooled down at room temperature for an hour, added a silane coupling agent to modify the surface to help improve the dispersibility and compatibility with the asphalt, as there are 2 materials with varying molecular weights. And then we dried again for about 2 hours at this 100 degrees centigrade, and then we also optimized our FRB blend. So I've taken out some of the results to discuss here because it's quite bulky research. So we, using the orthogonal design I've mentioned earlier, we were able to optimize that this 8th factor was the best for to yield the satisfactory results. So in order to create a flame retardant asphalt, we understand that we have to choose components that would have a wide range of reaction temperatures to be able to absorb the excessive heat in the surrounding and limit or prevent combustion as much as possible for as long as possible. So on your screen here, in the center here, is the thermogravimetric analysis of the base asphalt that was used. And there were 4 stages of mass loss. In the first stage of mass loss, we presumably it was the disintegration of the saturates and the aromatic fractions, the light aromatic fractions in the asphalt. In the second stage, the alkylic chains were presumably starting to break, which led to the what's called the disintegration of the longer chain hydrocarbons, and this led to the production of the gas. In this third stage, due to the gas that was produced in the second stage, we deemed it that it was here that most of the alkyls and hydrocarbons began to coagulate, and a lot of disintegration of the pyrolysis rather of the saturates took place here. Now, in the fourth stage was where we saw the most of the indecomposable ash and the carbon and the residue of person. So on your screen now is the TG thermogravimetric curves of the flame retardant blend constituents. Now on the left is the thermogravimetric analysis curve, and on the right is the derivative weight thermogravimetric analysis curve. So I'll use this one for the purpose of this presentation. So we noticed that the earlier picture showed the base asphalt had a temperature range from between 0 to 600. And by combining these 4 flame retardant materials, we've been able to expand that range of temperatures. They have a combined temperature reaction range of between 0 to 800, which is sufficient to cover for that asphalt. Now, we noticed that the first material, the expandable graphite, after being heated, expanded, as its name implies, rapidly, and thus was able to cover for the loss of the light aromatic fractions in the earlier stages of mass loss. because I told us earlier we had 4 stages. Now, the second, the magnesium hydroxide was able to react and then formed magnesium oxide and some saturates that were able to dissolve and able to reduce the concentration of the flammable gas and oxygen in this stage. In the third stage, the calcium hydroxide was able to form an insulating layer to prevent most of the smoke release. Now, in the last stage, the ammonium polyphosphate at the highest temperature range, and we presume that it was able to delay the combustion time for as long as possible. Now, after getting our flame retardant blend, we had to include a surface modifier, the KH550 silane surface modifier. And these tests were to optimize the percentage of the silane coupling agents that would be the best for the purpose of this research. And we notice here that the oil absorption, which is often related to the permeability, surface permeability of materials. However, it also depends on the amount of air voids present in the material. So by reducing the amount of air voids and ensuring better compatibility between the materials, we noticed that the oil absorption began to decrease. And at this point was the lowest, which presumably is the best for this silane coupling agent, which is between 1 and 1.2%. Also, the activation index is the relationship between the polar and non-polar components of this material. And we noticed that it continually increased until it got to around the same amount here before the increase began to slowly become negligible. So the 1.2% was chosen as the optimum silane coupling agent for the surface modification of this research. Now, we used infrared spectroscopy to examine the functional groups, and basically the silane coupling agent, this was before the addition of the coupling agent, the surface modifier, and this was after. So we noticed that obviously the peak or the economic peak here is weaker than that of the FRB blend because some of the silane reacted with the hydroxyl present in the FRB blend, and we noticed a new peak here at around 3413, which is presumably because of that reaction, because there was no especially new exothermic peaks that were found. Just this new peak here, presumably because of the silane reacting with the hydroxyls on the surface of the FRB blend after surface modification. Here we have the morphology using the SEM, the scanning electron microscopy. And on the left is the FRB blend of the asphalt before surface modification. On the right was the one after surface modification. So we notice there's a lot of coagulation that is visible here. However, following surface modification of the silane coupling agent, most of the free energy on the surface of the asphalt has been absorbed and better dispersibility was observed. After optimizing our FRB and FRB-SC blend, we had to test the performance, and we noticed that the penetration decreased, which is due to what's called the asphalt becoming more solidified, as most of the FRB-SC content was absorbed in the free asphalt. Then the softening point showed a clear increase too, which is close to the high temperature performance of the asphalt. And then the ductility reduced gradually, but was still within the specified limit. The limiting oxygen index, LOI, is basically the minimum concentration of oxygen required to sustain combustion on the asphalt in this case. And according to the Chinese national energy standards, for asphalt in the tunnels, it should be at least 23%. At 8% dosage, we know we were able to record an LOI of around 25.8%, which is easily within the specified limit. And it shows that the flame retardance of the asphalt has been elevated due to the addition of the FRB-SC flame retardant. Here, with regards to the rheology, we noticed from 0%, if you can see on this graph here, from 0% to around 8%, there was just a steady increase. and most of the increase was basically not really that much visible. However, after the 8% mark, there was an abrupt increase, which could be explained that the movement of the asphalt molecules became increasingly hindered, and there were more obstacles as more FRB SC flame retardant was added. So there were more particles in the asphalt, and therefore the flow became reduced, and thus the increase in viscosity. We performed temperature and amplitude sweep tests for the asphalt, and the base asphalt and the flame retardant asphalt. And we noticed generally, because there's not a lot of time, so generally we found out that the rotting resistance factor was increased, was improved, the complex modulus and the phase angle increased and decreased respectively. And the fatigue factor basically just decreased, it increased as the frequency increased. And naturally, within the for the temperature amplitude test, for the temperature sweep test, rather, in the lower temperatures, there were more visible changes. However, in the higher temperature regions, the changes became more negligible. The same for the temperature, for the frequency rather. In the lower frequency regions, the changes were very hard to see. However, in the higher frequency, which correlates to the temperature that way too, the changes were more visible. To the main crux of the research, which is the flame retardance of the asphalt, we have 4 indexes here, and the first one is the heat release rate. So the heat release rate is the, as we see here from the reaction temperature range, the blue here is the flame retardant modified asphalt that has been surface modified as well. So we notice that there are 2 major exothermic peaks, one here and one here. So the first one was quicker, however, the second one was larger, higher, and lasts longer. So it shows us that most of the decomposition and the combustion takes place in the middle to the latter stages of the combustion of the asphalt. And we noticed that by adding the flame retardant that was created in this research, we were able to reduce the height of the first exothermic peak, and also reduce more significantly, the length and the height of the second exothermic peak, making sure that lower heat was released. On the right here, we have the total, in the first place, we reduced the rate of heat release. And on the second picture here, we see that they all started with the same trend. And as the time went on, we noticed that the asphalt with no flame retardant was emitting more heat as time went on. However, with the addition of the flame retardant, we were able to reduce the total heat that was released at the end of the day, which would be directly proportional to the possibility for combustion in the asphalt. We have the total smoke release here on the left, and this shows the amount, as it's clear from the name, the amount of smoke that is released in the asphalt following combustion. And we noticed that the FRBS modified asphalt was able to produce an asphalt that would have a significantly lower smoke release. And lastly, and probably most importantly, is we know that CO, carbon monoxide, is responsible for around 90% of fire-related deaths. Especially here, we noticed that our flame retardant asphalt was able to reduce the total amount of CO that was produced. And this is really significant to the research. Yeah, basically this, I think my time is up, and this is the conclusion of the research. Says we were able to optimize the asphalt at this using the orthogonal experiment, and optimize the surface modifier at 1.2%. And the optimal content of our flame retardant was optimized to be around 8% by mass. When we compare this study to the currently used SBS modified asphalt in the tunnels in China, we can deduce that by adding this modifier to the asphalt, we will be able to improve the heat-related properties as well as the dangerous gases emitted during combustion. Thank you. I can't hear you, Mr. Joro.
Okay, unmuted ourselves. So any questions?